Moving on, we are going to look at the next section, looking at atoms that have formal charges in covalent molecules and ions. And you're going to be able to understand the meaning of atom formal charge and calculate the formal charge on each atom in a molecule or a polyatomic ion. Up to now, we've just been doing a lot of practice writing out the Lewis structures of molecules or polyatomic ions. You've seen these Lewis structures and you are able to see how electron pairs are placed in these covalently bonded species, whether it's in a neutral molecule or those polyatomic ions. But now we turn to one of the consequences of the placement of electron pairs in this way. Individual atoms can have a small negative or positive charge or have no electric charge. And you've probably done some different arrangements that are a little bit different than mine. And we're going to see how these arrangements can affect that. The location of a positive or negative charge in a molecule or an ion will influence, among some other things, but the influence the atom at which a reaction occurs. The formal charge is the electrostatic charge that would reside on an atom in a molecule or polyatomic ion if all bonding electrons are shared equally between pairs of atoms. The formal charge of an atom in a molecule or ion is calculated based on the Lewis structure of the molecule or the ion. We would calculate it by taking the number of valence electrons, and you'll see in your book it's abbreviated NVE for number of valence electrons, minus the sum of the lone pair electrons, or LPE, plus half of the however many are bonded electrons. Let's look at an example. Let's look at CH4, and let's calculate the formal charge of carbon in this compound. We need to take the number of valence electrons for carbon, which we know as 4. That's our NVE. Number of valence electrons is 4. We're going to minus, we need to sum up our lone pair electrons. And if you look around carbon, there are no lone pairs. And then we need to do half of how many of the electrons around carbon are bonded. Well, we've got 2, 4, 6, 8. So what's half of 8? 4. So 4 minus 4 is 0. So there is no formal charge on carbon. Let's calculate it for the hydrogens. Now all of these hydrogens are the same. How many valence electrons hydrogen has is 1. So we're going to minus the number of lone pairs that hydrogen has, none, plus 1/2 of how many bonded electrons does hydrogen have? 2. 1/2 of 2 is 1. 1 minus 1 is 0. So there is a 0 formal charge on hydrogen as well. Let's look at another example. This also pretty much tells me, since I have everything as neutral here, that ions are not going to be attracted. Positive or negative ions are not going to be attracted to any part of this compound. Let's look at the formal charge of carbon monoxide. We have CO. If we were to go back and think about how we drew CO in the last lecture, carbon we knew had 4 valence electrons and oxygen had 6. So there was 10 electrons that we were taking into consideration when we were making this compound. And then we drew carbon with a triple bond, 2, 4, 6 for carbon, plus the lone pair is 8. And then if I look at oxygen, that triple bond is 6, plus 2 is 8 for oxygen. So that was tricky to write it. Now, let's calculate and see what the formal charges of each atom. So let's do carbon first. We just said that there was 4 for carbon and 6 for oxygen. That's the number of valence electrons. Now we need to minus and look at lone pairs. Yes, oxygen had 2, carbon had 2. So we have 2 plus half of how many were bonded. Well, they're the same for both. 2, 4, 6 were bonded. Everything here is the same, but the difference is that carbon started with 4 valence electrons, oxygen started with 6 valence electrons. So 4 minus 2 plus 3 is 5. 4 minus 5 is negative 1. So this carbon formal charge on carbon is a negative 1. And on oxygen, we did 6 minus 5 to give us plus 1. The formal charge on my carbon, negative 1, so it would be slightly attractive to a positive ion on a different compound. And same with this one. This is a positive side, so it's going to be slightly attracted to a negative terminal. Note that the sum of the formal charges on the atoms in a molecule must equal 0. The sum of the atoms in an ion equals whatever the charge of that ion is. So if we go back and look at this last example, negative 1 and a positive 1 equals 0. We look at the example before that, This was 0 overall, so that didn't matter. We just covered this first one. The most plausible Lewis structure is the one with no formal charges, with the formal charges of 0 on all atoms. That would be the structure that would most likely occur. Where formal charges are required, they should be as small as possible. And negative formal charges should appear on the most electronegative atoms. For example, fluorine we know is the most electronegative element there is, right? So we would not expect a formal charge of a +1 near a fluorine. That probably would be unlikely. Adjacent atoms in a structure should not carry formal charges of the same sign. We don't want two negatives near each other. That would not likely occur. Formal charges on the atoms in a Lewis structure must total to 0 for the molecule and to the net charge of the polyatomic ion. So NH4 plus ammonium, the ammonium ion, should be a +1 charge when everything's added up. Consider the hypochlorite ions. Looking at oxygen to find its formal charge, we know that oxygen has 6 valence electrons. Then we're going to subtract my lone pair electrons. Oxygen has 2, 4, 6 here. 6 plus half of however many is bonded. We know that we have 2 bonded here. Half of 2, so 6 plus 1 is 7. 6 minus 7 gives me a formal charge of oxygen of -1. Now looking at chlorine, chlorine has 7 valence electrons. Again, there's 2, 4, 6 lone pairs and 1 bond coming off of chlorine, so half of 2 is 1. 6 plus 1 is 7. 7 minus 7 is 0. So there's a 0 net charge on the chlorine side and a -1 on the oxygen side. And remember, if it's not equaling 0, we need to equal what our ion charge is. Again, we made this compound, this Lewis structure, earlier in the lesson by taking chlorine and saying, okay, chlorine has 7 valence electrons, oxygen has 6. We have a -1 ion, so we need to add 1 more. So 7 and 7 is 14. And we took chlorine and we took oxygen. And we said, all right, chlorine has 1. There's got to be at least 1 bond between them. 1, 2, 3, 4, 5, 6, and this was chlorine 7. Oxygen, so this is 1, 2, 3, 4, 5, 6, 7, 8. Chlorine is happy. Oxygen has 1, 2 already. 3, 4, 5, 6, 7, 8. Now let's count our electrons. 2, 4, 6, 8, 10, 12, 14. And we know that this was a -1 charge. So to find that formal charge that we just did by taking valence electrons minus the lone pair electrons plus the bonded electrons, we found that oxygen had a formal charge of -1 on this end and the chlorine had a 0 formal charge. Calculate the formal charges for the atoms of the ClO3 minus. So looking at the ClO3 minus, calculate the formal charges of oxygen and chlorine. Hopefully you were able to find that oxygen and go, okay, yep, oxygen has 6 valence electrons. Find the chlorine. Know that chlorine has 7 valence electrons. So 6 minus, there are 6 electrons in the lone pairs around each oxygen. Plus 1/2 of each oxygen has 1 bond, which is 2. So 6 minus, 6 plus 1 is 7. 6 minus 7, the oxygens all have a -1 formal charge. Now let's look at chlorine. Chlorine we know has 7 valence electrons. Minus, chlorine has 2 electrons that are in lone pairs, so 2 plus 1/2 of 6. It has 1, 2, 3, 4, 5, 6 electrons that are in bonds. So 2 plus 3 is 5. 7 minus 5 is plus 2. So when I have a +2 and -1, -2, -3, +2 minus 3 gives me a net ionic charge of -1, which is what that ion is. Next, why don't you draw the structures for Cn minus and SO3 2 minus and calculate the formal charges on each atom. First, I drew the Cn minus. We knew that carbon has 4 valence electrons, nitrogen has 5. There's a -1, which means 1 extra electron, which is a total of 10. Drew it. Carbon needed 8. 1, 2, 3, 4, 5, 6, 7, 8 for the triple bond. Nitrogen also needed 8. 1, 2, 3, 4, 5, 6, 7, 8. And when we totaled it up, we've got 2, 4, 6, 8, 10 electrons. Now to find the formal charge, carbon. We're going to take number of valence electrons minus lone pairs. I'm actually going to do nitrogens at the same time. We know that nitrogen started with 5 minus, they each had 2 lone pairs plus 1/2 of, they each had a triple bond that they shared, so 1/2 of 6, 3. Half of 6, 3. So 5 minus 5, nitrogen had a no net charge. 4 minus 5, the carbon had a -1 charge. And again, it would equal 0, except for this compound has a -1 charge. So the formal charge on carbon is a -1 in this case. Looking at SO3, 2 minus, I calculated that each O was 6 valence electrons times 3, so that was 18. S contributed 6, and then we added 2 more because it was a -2 charge, so we needed 26 electrons. Each oxygen, of course, needed 8, so 2, 4, 6, plus the bond is 8, so 8, 16, 24. And sulfur was sitting in the middle with only 3 bonds, which was 6, so we needed to add the lone pairs for sulfur. Now let's calculate the formal charges. Looking at sulfur, we said that it had 6 valence electrons minus the number of lone pairs. There was only 1 lone pair, so 2 electrons there, plus half of bonded, 2, 4, 6, half of 6, which is 3. So 2 plus 3 is 5. 6 minus 5 is -1. So my sulfur has a -1 formal charge. Now let's look at the oxygen. Oxygen we know had 6 valence electrons also, minus, how many lone pairs did each oxygen have? 2, 4, 6, plus half of, there was only 1, each oxygen only had 1 bond. So half of 2. So 6 plus 1 is 7. 6 minus 7 is -1. Each oxygen, -1, -1, -1, +1. Therefore, I have 1, 2, 3 negatives, 3 negatives, and a +1. So -3 plus +1 gives me my overall ion of -2. Let's look and compare formal charges and oxidation numbers for hydroxide, OH. Again, to draw this Lewis structure, oxygen has 6 valence electrons, hydrogen has 1, and we know that it's a -1 charge, so it's got to add an extra electron, so we got to account for 8. Again, we know oxygen has 1, 2, 3, 4, 5, 6. Hydrogen has 1, so we know that we have a bond right here, and we know that we have that extra, so we need to have 4 pairs. Well, there's 1, 2, 3. We need to have our extra electron added there. So we have our 1, 2, 3, 4 pairs of electrons. Everybody's happy. Oxygen has 1, 2, 3, 4, 5, 6, 7, 8. Hydrogen has 2. We have a -1 charge. Now let's calculate the formal charge. Oxygen has 6 valence electrons minus, there's 2, 4, 6 that are in lone pairs, plus half of 2 in the bonded. So half of 2 is 1 plus 6 is 7. 6 minus 7 is -1 for oxygen. So we have a -1 charge on my oxygen side. And if I look at hydrogen, we have 1 valence electron minus 0 lone pairs plus half of, there are 2 electrons in that bond that hydrogen is attached to the oxygen, so half of 2, which is 1. 1 minus 1 is 0. Hydrogen's formal charge is 0. And if we look at both, I've got a -1 and a 0 to give me that overall charge of -1 for that compound. But now let's think and look back to what we know about oxygen on the periodic table. Didn't we say that oxygen had an oxidation number of -2 and that hydrogen was +1? Notice how the oxidation numbers are different from the formal charges that we just calculated. So here's the difference. Oxidation numbers are determined by assuming that the bond between a pair of atoms is ionic, not covalent. So for OH minus hydroxide, this means that the pair of electrons between O and H is located fully on O. So the O atom now has 8 valence electrons instead of 6, and grabbing 2 more to have that charge of -2. The hydrogen atom now has no valence electrons and a charge of +1. Again, if this was an ionic compound, the hydrogen would be giving away its electrons, not sharing it with the oxygen. So formal charges and oxidation numbers are calculated for different purposes. Oxidation numbers allow us to follow the changes in redox reactions, and formal charges provide insight into the distribution of charges in molecules and polyatomic ions. Why don't you try pausing the recording and try to determine the formal charges for the formate ion below. How about this one? What is the formal charge of the S atom in SO3? Take a second to draw it. Hopefully you got +2. What about the N atom in nitric acid? And the formula is HNO3 if you couldn't remember. So draw this out, find the formal charge on the N atom. I hope you got.
In this next section, we are going to look at how some molecules in polyatomic ions do not obey the octet rule, and look at how we can draw reasonable Lewis electron dot structures for those.
All right, now after all of that practice of checking to make sure that every atom was happy with having 8 and meeting that octet rule, and now I'm going to tell you that there's some exceptions to it. So the vast majority of molecular compounds and ions obey the octet rule, but there are exceptions. These include molecules and ions that have fewer than 4 pairs of electrons on a central atom, those that have more than 4 pairs, and those that have an odd number of electrons. So let's look at some examples, but for example, we're going to look at like odd numbers, NO, less than an octet would be BF3, and then there's more than an octet. Let's look at an example where a compound has fewer than 8 valence electrons, boron trihydride, so BH3 for example. We know boron, if we look at it on the periodic table, will have 3 valence electrons, and hydrogen has 1, and there's 3 of them, so this will equal 6 total electrons. So we make boron, hydrogen, hydrogen, hydrogen. So we will look to see, are there 6, 2, 4, 6? Yes, we are done. This is a trigonal planar molecule, and everybody's full and happy. There's a bond angle between all of these of 120 degrees. And that's just the way it is. So this is just one example of a molecule that does not obey the octet rule. So boron is a common atom that only allows for, since it has 3, so there's 6 electrons surrounding it. The other example is boron trifluoride. Again, boron is happy with just 2, 4, 6. Boric acid, another one where we could look at this and look at this oxygen, for example, and say 2, 4, 6, 8. This oxygen has 8, 8. This fluorine has 8, but boron is one of the exceptions where it's full with 6. I'm sure you've all heard of borax. Borax is a common mineral used in soap. I use it to make my homemade laundry soap, but the anion has 2 boron atoms surrounded by 4 electron pairs and 2 boron atoms surrounded by only 3 pairs. I thought this was an interesting video in the text to kind of show the reaction with BF3 boron trifluoride and NH3. And as you can see, we have boron trifluoride. Fluoride has 8. Each of the fluorides is following the octet rule. We know boron does not, but it can still form an octet. And here's an example of how it does.
Boron trifluoride is a Lewis acid because it has a deficiency of electrons. Ammonia acts as a Lewis base by donating its lone pair of electrons into BF3's vacant valence orbital. The product of this Lewis acid-base reaction is a single molecule with a new bond, called a coordinate covalent bond, because both the electrons for the bond come from only one species.
And this coordinate covalent bond is, in Lewis structures, it's often symbolized by an arrow that points away from the atom that's donating the electron pair. So similar to when we were showing our double bonds where the oxygen had to donate its lone pair electrons to form a bond so that everybody was happy. So that is something that happens, a coordinate covalent bond, when 2 different molecules are forming together, especially with boron, who is lacking electrons. Now, there are also compounds in which an atom has more than 8 electrons. Elements in the 3rd or higher periods can form compounds and ions in which the center element can be surrounded by more than 4 electron pairs. And there's an example, a picture I'm going to show you here in just a second. Here's also a little video to just kind of explain, and I'll talk about it more in just a second.
Now, there are some other molecules that have more than 8 electrons. On the periodic table, the second row elements that you'll see often is carbon, nitrogen, oxygen, and fluorine. These atoms cannot have more than 8 electrons, so they cannot have an expanded octet. However, they can have an incomplete octet. It is possible. Now, the elements below them, for example, like silicon, phosphorus, sulfur, chlorine, these elements, they can have what is known as the expanded octet. They can have more than 8 electrons. The reason why nitrogen can have more than 8 is because nitrogen is in the second row. And in the second row, you have the 2s sublevel and you have the 2p sublevel. Notice that in the second energy level, the maximum number of electrons is 8. So that's why second row elements cannot have more than 8 electrons. It's just not possible. Phosphorus is in the third row. So in the third energy level, you have the 3s sublevel, the 3p sublevel, and the 3d sublevel. So therefore, in the third energy level, you can have up to 18 electrons. And that's why elements like phosphorus, sulfur, and chlorine, they can have expanded octets. So if they're the center atom, they can have more than 8 electrons. Sometimes you might see them have 10, sometimes even 12. So just keep that in mind.
So here are some examples of those hypervalent compounds where the central atom exceeds an octet.
Now you still go
And
about
again,
building
if you
these
looked at
the
your
same
periodic
way.
table and
Let's
you
say,
looked
for
at
example, we
group
wanted to
four,
make
which was silicon,
ClF3.
germanium,
We would
so
still
we can
say,
see that we
okay,
can make
how many valence electrons
SiF5,
does
and
chlorine
here's what it
have?
looks like. We know that
7.
silicon has
All right.
4
How
valence
many does
electrons,
fluorine
but
have?
it's able
And
to
there's
make
3
1,
of them.
2,
Well,
3,
7
4,
times
5
3
bonds.
is 21. So we need to account for 28 valence electrons when building this. Well, we're going to have our chlorine as the center, and we're going to have 3 fluorines around it. Okay? Now we know, of course, there's going to be a bond to each one of those, so that accounts for 6 electrons. Now we need to start plugging in pairs to get to 28. We have 1, 2, 3, 4, 5, 6. And then this one would be 7, 8. So fluorine's good. Let's do this next fluorine. 1, 2, 3, 4, 5, 6, 7, 8. Let's do this next fluorine on top. 1, 2, 3, 4, 5, 6, 7, 8. Now if I stopped right there, there's only 24 electrons. So we need to do 25, 26, and then another pair, 27, 28. That would give me 28 electrons, but notice, I'm going to make a highlighter here, that I have 2 sets of lone pairs around this chlorine, and it's okay because I have to have 28 electrons accounted for. All of my fluorines are full with 8. Now, and it's okay that this chlorine has 2, 4, 6, 8, 10 around it. So it has an expanded octet.
Phosphorus we know has 5 valence electrons, and so 1, 2, 3, 4, 5, it's forming 5 bonds, but notice that because it's got 5 bonds, it's extended its octet, so it doesn't have 8, it's got 10. And same with sulfur. We can see that it has 1, 2, 3, 4, 5, again 10. Chlorine 2, 4, 6, 8, 10, and xenon 2, 4, 6, 8, 10. And anyways, here's just several examples where we are not following the octet rule and we have more electrons surrounding it. So these are referred hypervalent. And again, only elements of the third and higher periods in the periodic table form compounds and ions in which an octet is exceeded by the central atoms. The second period elements, boron, carbon, nitrogen, oxygen, fluorine, are restricted to the maximum of 8 electrons because they're in the second row. They can only have 1s2, 2s2, 2p6, so that 2s2, 2p6 they're limited to 8.
In this section, we are going to look at resonance structures. We're going to be able to draw them and look at simple molecules, polyatomic ions, understand what resonance means, and know how and when to use resonance to represent bonding. So equivalent Lewis structures that are the same except for the placement of where the electrons are is what a resonance structure is. That's when there can be more than one Lewis structure for one molecule. It also is when it contains double or triple bonds. Bond length is shorter than a single bond, but not as short as a double or triple bond. Resonance structures have the same arrangements of atoms, but just different arrangements of electrons. And the actual structure of the molecule is a composite or a hybrid of the equivalent resonance structure. For example, Let's say that I have O3, so I have ozone. Let's say that I wanted to draw oxygen, bonded to oxygen, bonded to oxygen. And we know that we have to look at how many electrons there are in these bonds. Each oxygen has 6 electrons, so 6 times 3 would be 18 electrons that we need to represent. Well, right here we only have 2, 4. So let's start putting electrons around our oxygens to get to 18. So 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, now we need to look and say, well, is everybody happy? This oxygen over here is happy. It has 2, 4, 6, 8. This oxygen over here is happy. 2, 4, 6, 8. But this middle oxygen right here only has 2, 4, 6. It needs more electrons. So we can do a couple of different things. We could take electrons from the oxygen on the left here, or we can take electrons from the oxygen on the right. And we can either take one set of lone pairs, doesn't matter which one, and we can bring it over here to form a double bond. Because if we take this set of electrons away and share it, this oxygen will still have 2, 4, 6, 8. And then the center oxygen, notice, will have our 2 lone pairs up here, 2, 4, 6, 8. We can either do that, which would give us this structure. Notice that the double bonds here would be on the left-hand side, or I can take electrons from the right oxygen. Again, it doesn't matter which lone pair of electrons, as long as I take one set of lone electrons and give it a double bond right here. So that would cross off. So I would have 1, 2 sets of lone pairs around this oxygen, and then we would have double bond on the right side. So that would give 2, 4, 6, 8. This right oxygen would still have 8. And now my center oxygen would still have 2, 4, 6, 8. And that would give me this structure. So resonance structures is just when I have a different place where I can put that double bond. I can put the double bond between these oxygens, or I can put the double bond between these oxygens. It's still O3. We still have the same number of electrons, 18 electrons that were accounted for. We're just changing the placement of where that double bond is. Let's look at another example looking at the carbonate ion. And carbonate ion is CO3 with a -2 charge. It tells us that there's 24 valence electrons. We could figure that out just by saying, well, we've got a carbon and 3 oxygens. So each carbon has 4, each oxygen has 6, so 6 times 3 is 18, and it's a -2 charge, so add 2 more, that would be 24 electrons. Okay, so if I've got carbon as my central atom with 3 oxygens around it, that represents 2, 4, 6 electrons. So let's just start adding in more. So we've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Looking at this, all of our oxygens are happy and they all have 8. But the problem here is that carbon is not happy. Carbon needs 2 more. And carbon doesn't have any lone pair of electrons up there because 24 electrons have been accounted for between this oxygen on the left, this oxygen going down, and this oxygen to the right. Therefore, to have carbon be happy and full, we either need to take electrons from the left oxygen and bring it over to form a double bond here, which would give me this structure. Or, if it doesn't do that and we go back to a single bond, we need a lone pair of electrons from this oxygen to form a double bond here, which would give me the second structure. Or we need the right oxygen to form a double bond on the right side. So these 3 are all resonance structures. They are all equivalent structures that can be drawn for this ion. The only difference is the location of where that double bond is between the carbon and the oxygen. Also keep in mind that wherever that double bond is, that bond is going to be a shorter bond than the single bonded carbon oxygens. Why don't you pause the video right here and draw resonance structures for the nitrite ion. Nitrite is NO2-. Are the NO bonds single, double, or intermediate in value. And think back to how we calculated formal charge. Find the formal charges on the N and the O atoms in those resonance structures. So pause the video here. Hopefully you found that there was 18 electrons to account for. 5 from the nitrogen, 6 for each oxygen, and there was 2 of them, so 12 for the oxygens. And then we added 1 more because it was a -1 charge. So if I just set it up with my N single bonded to an O, and I put all of my electrons around those oxygens on the outside, we would have the left oxygen is good and the right oxygen is good. But the problem is that middle nitrogen. And middle nitrogen only at this point has 2, 4, 6 electrons. It needs 2 more. But we can't add 2 more because we've already hit our 18 electron max. So therefore, I can choose to have my left oxygen donate one of those lone pair electrons to have O double bonded to the N, like this structure shows. Or I can have this right oxygen double bonded to the nitrogen to show this structure. And when I want to find formal charges, remember formal charge, if I wanted to find the formal charge on a certain atom, I take how many valence electrons it has. So let's look at this nitrogen down here. Nitrogen, I would say 5 minus, how many lone pair electrons are there? There's 2 plus 1/2 of how many are bonded? And there are 6. There's a double bond and a single bond, so 2, 4, 6. That would give my formal charge of nitrogen a 0 formal charge. And then, depending on whatever structure you choose, if you chose this one, we'll call it number 1, or this one, we'll call it number 2. The oxygen that has the double bonded side on it, we would say that it had 6 valence electrons minus 4 are in lone pairs plus 1/2 of 2, 1/2 of 4 because there's double bonds there, so 2, 4. So the oxygen with the double bonded side would have a formal charge of 0, and the oxygen that had the single bonded side, we would say its valence electrons was 6 minus 6 are in lone pairs plus 1/2 of 2 are in bonds. That would give me a formal charge of -1, which would make sense because remember, all of the formal charges for all of the atoms will equal the charge of the overall structure. And the overall structure here is a -1 charge. So 0 plus 0 plus -1 gives me an overall charge of -1. I would like for you to pause the video here and look at the resonance structure for carbon dioxide. So see, there will be 3 that you can draw, 3 different versions of CO2. Pause and see what you can come up with. Hopefully you came up with these 3 options. We could have number 1, where we have double bonds to both of the oxygens. We could have number 2, where one carbon-oxygen bond is a triple bond, and the other is a single bond. Or number 3 would just be the flip-flop opposite. The right side would have a triple bond, and the left side would not. Notice that they all have equal number of electrons. We just rearrange them. Now, remember we said the one that is most likely to occur will be the one with the formal charges in the correct spots. So let's take a second and find the formal charges of these 3 different resonance structures. Alright, I took a second and found all of the formal charges. If we look at our formal charge for the first one, I took the oxygen. Notice both of these oxygens are the same. The oxygen has 6 valence electrons minus both of these electrons have 4 electrons that are in lone pairs plus 1/2 of both of these oxygens have double bonds. So there's 4 electrons in double bonds. So 4 plus 1/2 of 4 is 6. 6 minus 6 is 0. Both of these oxygens have a formal charge of 0. And if I look at this carbon, I did 4 valence electrons minus. Carbon has no electrons that are in lone pairs. All of them are in those double bonds. So 1/2 of 8 is 4. 4 minus 4 is 0. This structure is the most likely, this resonance structure is the most likely resonance structure that we're going to see. Now 2 and 3 are options, but I want to show you why they're not probably going to occur. Notice that I could have a triple bond on the left. This oxygen on the left still has 1, 2, 3, 4, 5, 6, 7, 8. There are still 8 electrons that this oxygen has. It's happy. This oxygen on the right still has 2, 4, 6 in lone pairs, plus a single is 8. And this carbon has a single bond and a triple bond, so it has 8. And then number 3 is just the flip-flop of that. But let's look at the oxygen that's attached to the triple bond. So that could be the oxygen here on the left for number 2 and the oxygen on the right for number 3. Both of those oxygens attached to the triple bonds. Oxygen has 6 valence electrons minus each of these oxygens with the triple bond have just 2 electrons in lone pairs. So each of those oxygens has 2 in lone pair plus 1/2 of 6 that are in bonds. Each one of those triple bonds, right, is 6 electrons. So half of 6 is 3 plus 2 is 5. 6 minus 5 is a positive 1. And both of these, I would have a positive 1 formal charge where that oxygen triple bond of the carbon is. Now let's look at the oxygen with a single bond. So that would be this guy and the one on the left. The oxygen with a single bond. Oxygen has 6 valence electrons minus, with those single bonds, there are now 6 electrons that are in lone pairs. 2, 4, 6, plus half of 2. There's only a single bond, so that would be 2 electrons. 6 plus 1 is 7, so 6 minus 7 is a negative 1. So on one end of this compound, I would have a positive 1, and the other end, I would have a negative 1. And then my carbon in the center, 4 valence electrons, there's no lone pairs, and there's all bonds surrounding that, so half of 8 is 4. 4 minus 4 is 0. Each of the carbon is 0, but again, if one end is a positive 1 and one end is a negative 1, we prefer, the atoms prefer, to have the least formal charges. And in number 1 case, they all have the formal charge of 0, so that's going to be the easiest for it to choose. All right, this is our last example we're doing together before I have 2 practice problems for you, and that's the end of this lecture. Can you write the resonance structures for dinitrogen monoxide, N2O? Pause the video here and find the 3 resonance structures for this. And in addition to that, find the formal charges for each of the 2 N's and the oxygen. Let's see how you did here. We would have found first, it's important, number 1, to find out how many electrons are we accounting for. And if we have 2 nitrogens, that means we have 5 valence electrons for each. So 5 times 2 would we have 10 electrons there, plus the 6 oxygens valence electrons. So 16 total electrons in these structures. N2O, so we have an N, an N, and an O, and when looking at this to make sure that there's 16 electrons, there's 2, 4, 6, 8. That oxygen's happy. This nitrogen is happy in the center because it has 2 double bonds, so 12, 14, 16. There we go. Informal charge that on this nitrogen would be a negative charge, the center positive charge, and on this oxygen would be a 0. Another option, we could form a triple bond between these 2 nitrogens, giving me a 0, a positive 1, a negative 1 charge. And then flip-flopping this structure over here, I could have a triple bond on the right side, giving me a positive, and a negative 2. Which one do you think would be the most stable resonance structure? Well, if we look at these structures, notice that this bottom one, we would have a negative 2 charge on this one end of the structure versus a positive and a positive, and this is going to be a pretty large formal charge. This is probably not going to be very stable. If we look at the 2 above it, we can see that while we have a negative and a positive on the right side, a negative and a positive on the left side, they both are pretty similar as far as formal charges, and they're both going to equal to 0, but I would think that the 2 double bonds would be easiest for this molecule to make. However, oxygen is the more electronegative of the 2 between oxygen and nitrogen. So it probably is a pretty equal split on which one of these structures is most stable. Now, since we just did that, let's look at this join-in question. Which one is not a correct Lewis resonance structure for the N2O molecule? Hopefully you would look at this and say that this would be a correct answer because this nitrogen cannot have 3 plus 2, 5 bonds, that would be 10 electrons. That would not work. And if you want to pause to see which one would not be a correct Lewis structure for the HCO2 minus ion, hopefully you would see that it is this guy. Again, my central carbon cannot have 1, 2, 3, 4, 5 bonds coming out of that central part. That would be 10 electrons coming out of carbon. And that is just not feasible.